actually. Which row describes the boiling and the evaporation of a liquid? This one's pretty straightforward. We know that boiling has to take place at a specific temperature. Why? Because that is dependent on the chemical structure or chemical bonding of the material that you're looking at. So it cannot boil at different temperatures. That would not make sense. Evaporation, on the other hand, can take place across a range of temperatures. And we also know that it has a cooling effect. So in the case of boiling, yes, bubbles do form. In the case of evaporation, we have cooling. Also, from personal experience, I'm sure all of you categorically know that evaporation does not produce any boiling. When you see a puddle of water outside drying under the sun, clearly there's no boiling. So there are many cases in which you can use everyday experience to actually just pick the right choice. One thing I'm just going to mention here is that when we talk about evaporation, what's happening is that all of these molecules at the surface of the liquid are escaping. And when they escape, what does that mean? Is that the total or the average kinetic energy left behind falls. When that falls, what does that tell you? That the temperature falls. If the temperature falls, what does that mean? It cools down. So again, you see there's a lot of variation in terms of how people learn physics. What I'm trying to show you, I mean, in 1 hour, I can only do so much, but what I'm trying to demonstrate to you that physics, out of all the sciences, it lends itself the best to critical thinking, just logical reasoning. So when you're reasoning with yourself as to what's happening or how to answer a question, you just ask yourself questions in stages like this, right? That, okay, if some molecules have left, what does that mean? Okay, if they're the ones with the highest kinetic energy, what does that mean with regard to the liquid that's left behind, that the kinetic energy falls? If the kinetic energy falls, what does that mean? That the temperature falls. So you see, you can go in very clear logical steps like that to work your way through the problem. Okay, so this one, a hairdryer is used to blow air across the surface of water in a beaker so that the water evaporates. What increases the rate of evaporation? Again, you need to underline that so that you're not confusing it with a decreasing rate. Why does that happen? Because when you're taking the exam, you're a little more stressed than you would be otherwise. It's very easy to get distracted. Doing this will prevent that. Okay, so rate of evaporation, what do we know about that? If we increase the surface area, for example here, let's say we're looking at this beaker or container, more molecules obviously will be able to escape at any given time, which means rate of evaporation is going to be higher. So that's one of the easiest ways to increase the rate of evaporation. And that's actually what they've given as well. Decreasing the speed of the air from the hairdryer, this is actually going to decrease the rate of evaporation. Decreasing the mass of the water in the beaker, the mass of the water in the beaker has nothing to do with the rate of evaporation. Why? Because evaporation does not take place throughout the liquid. It's only at the surface. So the mass is not going to impact that. Increasing the volume of the water in the beaker, again, the amount of water or the volume in the beaker has nothing to do with the rate of evaporation. 24, we have a ray PQ reflected by mirror X, right here, to a parallel mirror Y. The reflected ray along RS is parallel to PQ. So along RS, these two are parallel. Now it says which statement is correct. Now, what I would do if I were you, the first thing, in the case of reflection, you're interested in angles, right? So angle of incidence and angle of reflection. So let's just do that. We add a normal to the mirror there, add normal to the mirror here. Now we know that this is angle of incidence, this is angle of reflection. Same thing here, incidence and reflection. What do we know about reflection? Is that the law of reflection holds true for all of these rays. What's the law of reflection? Simply saying that the angle of incidence should be equal to the angle of reflection. And now we can see which one looks right. So angle between PQ and QR is 45. Of course, that's wrong, easily eliminated. QR and RS, again, it's not 180 degrees, so that's out. We're left with the bottom two. If the angle of incidence of PQ on mirror X is 60 degrees, meaning if this is 60, then this would also have to be 60. The total angle will be 120. but that's not the case, clearly. So that's also wrong. D is correct. Why is it correct? Because the angle of incidence is actually 45. How do we know that? Because if this is 45, we do know that this must be 45 as well. What's the total? 90. And that is a 90-degree angle. So again, on this paper, make sure, unless you're really stuck and having trouble, you're having trouble working your way through problems, there's no guessing needed whatsoever. All right, so over here, I'm not going to read the question just to save time. How does the image compare with the question? What do we have? We have a lens and we have this arrow as the object. We have two rays. This one goes here and then travels like that after passing the lens. And then this one goes straight. Why does this go straight? Because, again, I'll remind you of something that's important, is that the optical center of the lens is right here. Whenever a ray goes through the optical center of the lens, it does not deflect or it does not bend. So it just goes straight. Now, how do we see how we want to do this? It's actually pretty straightforward. This is, so when the rays are passing through the lens, they're clearly diverging. They're not going to meet on this side of the lens. Let's now look at the left side of the lens. If we extend them backward, we can clearly see that they're meeting at this point, which means that that is where the image is going to be formed. So I can just do that. Let's just draw an arrow. Oh, this is actually, yeah, drawing vertical lines is challenging when I'm using the tablet. All right, so that's your image. And now you can simply compare. There's no need to remember anything. All you need to know is that's where the image is going to be formed. Well, how does it compare to the object? It's obviously upright. Why? Because both arrows are pointing upward. It's larger or it's magnified, clearly has a longer length, and it's on the same side of the lens as the object. So there you go, you just pick the right one. It is larger and it is upright. So in a question like this, there's no memorization needed. You just quickly draw it and match. All right, so violet and indigo light have the shortest wavelengths in the spectrum of visible light. Which three colors, in order of increasing wavelength, immediately follow indigo? Now again, be very careful when you're reading a question like this. The first statement is giving you the order of, is saying shortest wavelengths. Then the second statement is saying, what's the order of increasing wavelengths? So you see, you're going in both directions. So be careful with that. So what's the order? You'd have to just write that out. And what's the order of increasing wavelength? It's towards the red end of the spectrum. That's increasing wavelength. So these are the two that they're talking about. What are the next ones? B, G, Y. What's that? Blue, green, yellow. That should be easy. You can do it in like 20 seconds. So we have a sound wave in question 27. It says, which type is it and what is at X? It's pretty clear that if you look at this section and then this one, alternating sections, these are called rarefactions. Why? Because the particles are further apart. And this one is called a compression. So X is clearly a compression. And there you go. We know, again, just to quickly remind you, a transverse wave is one where the vibration of particles is at right angles to the direction of movement. So if a wave goes to the right, particles vibrate like this vertically. So this is vibration, and this is the direction of the wave. They always form a 90-degree angle in the case of transverse waves. In the case of sound, the vibration and the direction of the wave, they are aligned. And what happens in these regions actually, because they're closer together, that's actually telling you something about the pressure as well, which means that if you're asked about pressure in a similar question, you should be able to answer it, meaning that the pressure here is higher and the pressure in the case of a rarefaction is going to be low because they're further apart. So that's the connection. 28 is actually a very interesting question. It says a man stands between two tall buildings, P and Q. He's 50 meters from P and 200 meters from Q. Both of those are shown. He sounds a horn. He hears the first echo from building P, obviously because P is closer to the person. And 1 second later, he hears the first echo from building Q. What is the speed of sound calculated using this information? Now, when you're generally calculating the speed of sound, what do you need? You simply need distance and time. Now, the problem in this question is that over here, we have the distance, we don't have the time. Same thing here, we have the distance, we don't have the time. We do have some kind of time that's given, which is 1 second. Now, the most technical thing in this question is probably to understand what that time exactly is telling you. So let's read that again. He hears the first echo from building P, and 1 second after he hears that echo, he hears the second or the first echo from building Q. Now, what do we know about what's happening here? Is that the sound on the left is going to travel 50 meters to the left, 50 meters to the right. So what's the total distance it'll cover? 100 meters. The sound on the right is going to go like that and return. So 200 to the right and 200 to the left. Total distance is going to cover 400 meters. Now, at the instant where this person hears the echo from building P, how much distance will the sound cover? 50 and 50, 100. Now, obviously, if the sound on the left is covering 100 meters in some time, then the sound on the right is also going to cover the same distance in the same amount of time, because obviously it's just sound, so traveling the same speed. So it covers 100 meters over here. Now that's the instant where echo from P is heard. So let's just do a bit of a thought experiment saying that we are paused in time. Okay, so just imagine we're paused in time and the echo has just reached us. Now, when I hear the echo from P, the sound on the right has also traveled 100 meters. So how much more does it need to travel in order to reach me from Q as well? It needs to travel 300 meters after I hear the echo from P. And how much time does it take to cover this distance? It is 1 second. So then what's the speed? 300 meters divided by 1 second. The speed of sound is 300 meters per second. And this is a very good question. So you've probably already done it yourself, but it will really help you if you can nail this question conceptually. So you cannot use information on either side of the person to solve the question. They both need to come into play. And that's exactly what you had to figure out. Well, one of the uses of ultrasound, well, cleaning jewelry is clearly one of the choices. Why does that happen? You know, ultrasound is very high frequency, has a lot of energy. So if you have a pencil where, let's say, you have some kind of jewelry particles on it and you have some dust, if you just put ultrasound on it, you know, there's vibration that's going to take place and it just causes the unwanted stuff to fall out. Question 30. A positively charged rod is held near an uncharged metal sphere on an insulating stand. What is the distribution of charge on the sphere? Well, this is pretty straightforward. You have a positive charge here, so you're going to attract negative over here, and then the other side is going to be oppositely charged. So that should be pretty straightforward. What we need to make sure that you understand is that how come we keep talking about these insulating stands all the time? The answer to that is very simple. If you were to use a conducting rod, a rod over here that conducts electricity, then you're not going to be able to isolate the charges inside the sphere. You're going to lose them. They'll get neutralized. That's why we always mention this part, which is the insulation.